In this video, I just wanted to emphasize two important points that I think are really helpful for you to remember about potential and electric field and how they're related. The first point is the idea that electric field lines will always point in the direction of decreasing potential. And the second point that I want you to remember is how are the equipotential surfaces oriented relative to the electric field. So one of them is a fact, the second one is a question which we will answer. So what I drew here is the representation of a uniform electric field that's pointing to the right. And I'm imagining that we move from point A to point B in this electric field. Now, we learned that as we move around in an electric field, there's the potential to experience a change in potential. The change in potential is equal to minus the integral of the electric field with the displacement. Now, in this scenario, I could move from point A to point B along a very straight line, or I could, choose some sort of meandering path at the same, in each case getting from point A to point B. Because the electric field in this scenario is strictly pointing towards the right, then only the displacement along that direction is going to contribute to the change in potential. And so because the electric field points to the right, it's just really, I could call it dx would be my displacement. Notice I've gotten rid of the dot product because the only dl that's going to give me a non-zero contribution would be that is in the x direction, which corresponds to the horizontal electric field, which is also in the x direction. Now, I've already said that the distance between point A and point B is going to be called d. And so we're going to just say this is equal to E times d. And this is going from A to B. This is delta V, which is going to be VB minus VA, remembering that when we see the change in anything in physics, it's always the final minus the initial. And final is my point B, my initial is point A. So VB, sorry, I forgot my negative sign, that's really important, minus VA is equal to minus E times D. So what this is telling me is that my delta V is less than 0 because of that negative sign, which means that VB minus VA is less than 0, which means that VB is less than, VA. So in moving from point A to B, I've moved from a point of higher potential to lower potential. I've moved with the electric field, and again, what this is showing me, and this is a conclusion that I want to remember, is that the direction that the electric field points in is also pointing in the direction of decreasing potential. If I wanted to give them numbers, I might say that at point A, VA might be, say, 10 volts, and point B might be 6 volts, just to sort of put it in perspective or to attach some numbers to it. Okay? So, again, I think that this is a really handy thing to remember. Again, electric field points in the direction of decreasing potential. Now, using this relationship, we can answer the other question, which says, how are the equipotential surfaces oriented relative to the electric field? And so I'm asking myself, for instance, how could I move around in this electric field to give a delta V equal to 0? That would mean that, let's say, I go between 2 points with the same potential. So if I want delta V to be equal to 0, which is equal to minus this E dot dl, I might ask myself, how does this dot product become 0? And we might remember that when we take the dot product of two vectors, it's equal to 0 if they're perpendicular to each other. And so the idea is that I will find equipotentials are going to be perpendicular to the electric field lines. And so I might draw those dotted pink lines represent equipotential lines. That is, anywhere along that line has the same potential. We could say that this is the line of 6 volts, this is the line of 10 volts, this might be 8 volts. And it means that anywhere along those lines the potential is the same. It also would mean that if I moved anywhere in this vertical direction along this line, it would be easy because there would be no change in potential, therefore no change in potential energy. No work would be done in moving along that equipotential line. And so that's how we get the answer to the second question, which is how are the equipotential surfaces oriented relative to the electric field? The answer is that they're perpendicular to them. I just think that these two facts are really handy to remember. Just little things to keep in our mind that we should remember.